Now let us read the problem and draw a diagram which would actually put all these values into that diagram. It's a steel plate of width 120 mm. So there is a steel plate whose width is 120 mm. So let us draw this steel plate something like this. It's a steel plate something like this, and width is 120 mm. This is 120 mm. And the thickness is 20 mm. So this is the thickness T. So that is thickness is 20 mm. Okay. So we are referring to this plate. So we are referring to this plate here. And now this plate is bent into a circular arc of radius 10 mm. So that means we are applying a moment here. So we apply a moment on this beam so that this beam bends into a circular arc. So let me actually show it like this. It actually bends into a circular arc something like this. Circular arc. Now this beam bends into a circular arc of 10 meter radius. So that means if you actually draw a perpendicular from these two ends, so that means if you draw lines like this from these ends, here, this goes and meets here, and this distance will be equal to 10 meters. So this refers to R. You know, m by I is equal to sigma b by y is equal to E by R. So we had not used any equations, I mean that equation for any term related to R. It is the first problem with this. So R is actually 10 mm. And determine the maximum stress induced and the bending moment which is acting on the beam. So first let us find out the maximum stress induced. So now let us find out okay, first let us write the formula. Now what is the formula, guys? May I sing for you? Ilayaraja. Okay, out of this, so first here they are asking what is the stress induced. So what is the stress induced? So they are asking this, and they are given this. So they are given this. They are given this. So we know that y is nothing but the distance between what? The neutral fiber to this. If you know the thickness, then we can find out y, which is equal to d by 2. So therefore y is also known. So in this, only the sigma is not known, E is known, R is known, y is known. So therefore we can use this part of the equation now to find out stress. Then we can actually use this formula to find m. So let us find out these values now. Sigma, which is not known, sigma b, divided by y. Y is how much, guys, basically? 10. So this is actually, okay, it is a neutral axis. So this is equal to 10. So y is equal to d by 2, that is 10 mm. Okay. And Young's modulus is equal to 200 GPa. So 200 GPa is 2 into 10 to the power of 5 Newton per mm square. So this you're already familiar because we have converted this many times like this. And then divided by R. R is equal to how much? 10. Most of the students substitute this value and start doing with the calculator. They go completely wrong because here it is mm, here it is meters. So you need to convert this into millimeters to go further. Okay. And then here, anyway, this is in Newton per mm square. See the consistency in the units. Here it is Newton per mm square divided by mm. Here it is Newton per mm square divided by m. So that means now to balance this equation, this has to be Newton per mm square. So that means whatever you are finding here, the answer is in Newton per mm square. Okay. So find out this sigma b. Guys, what is the value of sigma b here?
0.0.
Please again check. See, it feels like here it feels like here 10 to the power of 5, this is 10 to the power of 4, cancels.
200.
So this is actually cancelling with this.
200.
Okay.
200.
So it is 200. So you got it as 200 Newton per mm square. So sigma B, you got it as 200 Newton per mm square. Okay, then you also can use this equation. Then you can also use this equation to find out the next part, that is, here they have asked what is the bending moment introduced. So for this stress, now for this stress or acting on the beam. So you know the stress here, so sigma d by y. So we'll use this part of the equation now. So maximum bending moment. Now maximum bending moment they have asked m, which I don't know. Now for this beam, this is the cross section. It is the cross section of the beam. So that means we know the beam looks like this from the end. So B is equal to how much? 120. D is equal to how much? 20. So we know I is equal to BDQ by 12. So I is equal to how much? B is equal to 120 mm. D is equal to 20 mm. 20 mm to the power of 3 divided by 12. So I is equal to how much?
80,000.
Huh? 80,000. 80,000, what is the unit? M to the power of 4. So m to the power of 4. I is found out now. Okay? I is found out. So here 80,000 millimeter to the power of 4 is equal to sigma. Now for this we already found out sigma here. Now as per this we already found out sigma here. So that is 200 Newton per mm square divided by y. So how much is y? How much is y? 10 mm. So you find out m now. So that will give you. So here you will understand that m has to be in terms of Newton, millimeter or meter. So everything is expressed in millimeters here. You get it as force into distance, Newton into millimeter. So you get it in Newton millimeter. Here also you can see here Newton millimeter divided by m to the power of 4. It will become Newton divided by m cube. Here also it is consistent. M cancels out. You can see here the consistency is same. You can remove this and make it as Newton per millimeter cube, something like this. So unit is consistent. Now what's the answer, guys?
16 lakhs.
16?
Lakhs.
16 lakh. So 16 lakh.
Newton.
So 16,000, 1.6 lakhs. So 16 lakh. So if you don't want, so this is in Newton millimeter. That means for nm, so you need to apply so much of moment for 1 mm. But if you want to convert that into millimeter, then it becomes 16. So how many zeros are gone? So 3 zeros are gone. So you can write it as 1,600 Newton meter. Or still, if you want to make it look familiar to you, so it will be 1.6 kilonewton meter. Okay? So this is a familiar unit, kilonewton meter. So this is how you solve this numerical.